The following video is over trigonometric leveling calculations. We're going to start with the trigonometric ratios sine, cosine, and tangent. Notice that I have two right triangles here. One's in green and one's in blue. But the green triangle is using a zenith angle, whereas the blue is using an altitude angle that we will be calculating in, use for our calculations in the trigonometric leveling. Now, the equation sine is opposite over hypotenuse. So for the green, the opposite is going to be the horizontal distance, and the hypotenuse is the slope distance. For both the blue and the green triangle, the slope distance or the hypotenuse is the same line. The cosine of the angle is the adjacent side. So for the green, the zenith angle, the adjacent side is the vertical distance, and the hypotenuse is still the slope distance. For the tangent, we're going to take opposite over adjacent. So when we're looking at this, we can either say the sine of zenith is equal to the hypotenuse or the horizontal distance over the slope distance. Or we can rearrange the equation to solve for the horizontal distance. Cosine of the zenith angle is the vertical distance over the slope distance. Or we can say we're going to solve for the vertical distance using the slope distance times the cosine of the zenith. Now we're using the zenith is because this is what the total station will actually read on the screen. It'll be called the VR angle. The tangent z of the zenith angle is going to be the horizontal distance over the vertical distance. Rewriting this, we can say the horizontal distance is the vertical distance times the tangent of the zenith angle, or we can say and solve for the vertical distance is equal to the horizontal distance divided by the tangent of the zenith angle. Calculating the difference in elevation between points is accomplished with trigonometric leveling. Differences in elevation are determined by measuring vertical angles and slope distances. Trigonometric leveling is often used where accurate elevations are not available or when elevation of an inaccessible point must be determined. So when we're looking at this, these are all of our parameters that we'll be looking at. The total station will actually give us a vertical distance, horizontal distance, and a slope distance. Some machines may not. We're also going to be looking at the change in elevation from point A to point B. We have an instrument height set up over point A, and we have a rod height where we have over point B. The equations that we're going to be using could be entailed the vertical distance equals slope distance times cosine of zenith angle. We're only going to be looking at the zenith angle in these problems. We will not be looking at the altitude angle, but be aware that you can actually solve it because the zenith angle and the altitude angle actually make a 90-degree angle. So we're going to be using the vertical distance is equal to the horizontal distance times the cotangent of the zenith angle. Now, cotangent is just 1 over the tangent of zenith angle. And the elevation, when we go to solve for the change in elevation from between point A to point B, we're going to use the instrument height at point A plus the vertical distance minus the rod height. All right? So those are our equations. Now, for short distances up to about 1,000 feet in length, elevation differences obtained in the trigonometric leveling are appropriately depicted by this figure. However, the longer the distances, we'll actually have to take into account curvature and refraction. That'll be discussed later. So here's an example. The slope distance in the zenith angle observed from point A to point B was 321.92 feet. So that's the slope distance S. And the 81 degrees, 36 minutes, and 46 seconds is the zenith angle, this angle here at Z. The instrument height is 4.1 and the rod target height is 5.0. So we have an elevation at point A of 126.66 feet above the datum. So we want to figure out what the elevation at point B is. So this is the data that we have. So we fill out the information. So the slope distance here is from point A to point B is 321.92 feet. The zenith angle here is the 81 degrees, 36 minutes, 46 seconds. The height of the instrument is here, and it's 4.1 feet, and the rod height here is 5.0 feet. Now, the elevation actually right here is the 126.66 feet. The equations that we're going to be using is we're going to solve for the vertical change, and then we're going to solve for the change in elevation. We'll use those two equations to solve for the elevation at B. So here's the equation. The vertical distance is equal to slope distance times the cosine of the zenith angle. Plug in our knowns, and then we'll get a vertical distance of 46.956 feet. That's this distance here. The change in elevation is the instrument height plus the vertical distance minus the rod height. So 4.1 plus the 46.956 minus 5 feet gives us a change in elevation. The elevation change from this point to this point, notice from A to B, is 46.056 feet. Therefore, if I know that the elevation at A is 126.66, I'm going to add the 46.056 feet, and I'm going to come up with the elevation at B of 172.72. Now, the next example is where we've got a slope distance and a zenith angle from point A to B is 321.92 feet, and the zenith angle is 98 degrees, 45 minutes, and 16 seconds. The instrument height is 4.5 feet, and the rod height is 5.1. And we know the elevation at A is 103.66. Now, notice that I am having a different picture here. Once we get past 90 degrees for our zenith angle, this would be the 90 degrees, we'll be looking downhill. So if we're looking downhill, then the vertical distance is going to give us is going to be a negative value. So if you know your zenith angle is greater than 90, then the vertical distance value calculated is going to be a negative number. These are the equations we'll use. The vertical distance is equal to the slope distance times cosine of the zenith angle. And the change in elevation is the instrument height plus the vertical distance minus the rod height. Note again, the vertical distance when you're looking downhill will be a negative number. So we're going to plug into our equation the vertical to solve for the vertical distance. We have 321.92 times the cosine of 98 degrees, 45 minutes, and 16 seconds. This gives us a negative 48.996. Remember, I said we're looking downhill, therefore this value here is going to be negative. The change in elevation, HI plus V minus R. Notice I have a negative value here, so I am subtracting. So that's going to give us a negative 49.596, which makes sense because we are looking downhill, so the elevation is going to be less than the elevation we are currently at up here. Now, the next point is the elevation at point B is we're going to take the 103.66 feet and subtract the 49.56 feet, gives us 54.06 feet. That's the elevation at B. Now we're going to go into an example of using the trigonometric leveling without taking into account the Earth's curvature and refraction and calculate from the field data below the northing, the easting, and the z elevation of point 2. So this is data that we would be collecting out in the field. So we have a known point, point 1, that's where our instrument's at, and it has a northing, easting, and z elevation of 800 for the northing. The easting is going to be 1500 and the z elevation is 72. Notice that it is northing, easting, and z elevation. So we're actually saying y, x, and z. Just remember the order that we're putting these in. Now we're backsighting the point of azimuth, point 99, and it's got a northing of 914.79 and easting of 1,362.25, and we don't really need the z elevation off of that because we're actually calculating the points to determine the azimuth from point A to the azimuth point. Now, the instrument, when it's at point A, we backsight the zenith or the azimuth angle, and we sight to point 2. When we sight to point 2, the horizontal angle is 75 degrees, 45 minutes, and 18 seconds. The instrument height is 3.86 and the rod height is 5.2 2 feet. The zenith angle is 96 degrees, 10 minutes, and 20 seconds, and the slope distance is 155.62. So to solve this, we're going to use the horizontal distance between the 2 points using trigonometric leveling and the method of side shot calculations to determine the northing and easting. Now, let's go ahead and set up the information to do the horizontal distance for the trigonometric leveling. So we know based on our zenith angle of the 96 degrees, 10 minutes, and 20 seconds, we're looking downhill. So we have the slope distance of 155.62, the instrument height of 3.86, and the rod height of 5.2. The elevation is 72. Now when we start to put this information in, these are the equations that we're going to use. Now because we have the slope distance and we need the horizontal distance for our side shot calculations, we'll have to solve for the horizontal distance in addition to the vertical and the change in elevation. So we start to plug in our equations and we solve for the vertical distance. So we have 155.62 cosine of 96 degrees, 10 minutes, and 20 seconds, and we get a vertical distance of negative 16.732. We know that it's negative because we are looking downhill. The change in elevation is going to be 3.86, the instrument height, minus the 16.732, minus 5.2, giving us a negative 18.072. That means at point 2, we're going to take the 72 elevation at point A in this, or point 1, and subtract off the 18.072. So the elevation at point 2, or point B, is 53.93 feet. Now we have to solve for the horizontal distance. So we're going to take the vertical distance of negative 16.732 and divide it by 1 over the tangent 96 degrees, 10 minutes, and 20 seconds. 1 over the tangent of an angle is actually the cotangent, but we don't have cotangent in our calculator, we just have the tangent. So when we solve this, we figure out the horizontal distance is 154.718. Now, if you get your horizontal distance greater than your slope distance, you know that you've made an error, because the hypotenuse is always the longest length in a right triangle. Now in step 2, we're going to use the method of side shot calculations to determine the northing and the easting. So the solution is, we know the x, y, z, the northing, easting, and z elevation of point 1, and the northing and easting of the azimuth angle that we're taking. So the horizontal distance and angle that we've taken is 75 degrees, 45 minutes, and 18 seconds. This is information would it be collected out in the field during the field exercise. The horizontal distance of 154.718 is actually taken from the previous calculations in step 1. So let's draw our picture. So we're here at point 1. We're here at point 1 and we're set up here. We are backsighting to the azimuth point 99, and we are turning an angle to the right to point 2. So the equations that we're going to be using is we have to figure out the departure and the latitude. The departure is the horizontal distance, and we've solved for that, the horizontal distance times the azimuth of the point from point 1 to point 2. So we need to solve for this azimuth angle right here, okay? And the latitude is equal to the length, the horizontal distance of 154.71, times the cosine of the azimuth from point 1 to point 2. So again, this is our azimuth that we'll have to solve for. So the last equation that we'll need is to determine what the bearing is. We're going to take the inverse tangent of departure over latitude. So first thing first is we need to calculate the azimuth from point 1 to point 99. So we need to calculate the azimuth point from here to here. And to do that, we've got two coordinate points, and we can solve for the azimuth. First, we'll have to solve for the change in the departure and the change in the latitude. When I say change in departure, it actually means am I going east or west, and the change in latitude, am I going north or south? So I'm going to take the eastings for the departure, which is 1,362.25 and 1,500. Subtract those two, and I'm going to get a negative 137.75. It's negative, I'm going west. The latitude is going to be the 914.79 minus the 800, and that is going, the change is 114.79, and I'm going north. Remember, when departure is negative, if I'm going from point 1 to point 2, and I draw myself a picture, I can visually see I am going west and I'm going north from point 1 to the point of our azimuth. Okay? Now I'm going to erase all that. So here's the picture. Here's the departure. So you can visually see that the departure is going a negative 137.75 and the latitude is going 114.79. All right? Now, the bearing from point 1, basically the bearing is from point 1 to point 2. The bearing is actually going to be telling me this distance here because I'm going from point 1 to point 2. I'm actually going in a northwest. I'm going in a northwest direction. Okay? So I'm going to take the tan inverse of a negative 137.75 and divided by 114.79. So I'm going north 50 degrees, 11 minutes, and 41 seconds. Okay? So, and this arrow's flipped backwards, so the arrows should be pointing this way. Okay? So from the north, I am moving west 50 degrees, 11 minutes, and 41 seconds. Now, I actually want the azimuth. All right? Now, I'm going to clean this up so you can see the sketch. Again, I should have had this going this direction and not that direction. So the azimuth is actually going to be going, when we solve for the angle of the azimuth, we're going from a 0 degree line, the purple rotation, a 0 degree line all the way around. So when I take 360 degrees minus 50 degrees, 11 minutes, and 41 seconds, that azimuth angle is actually 309 degrees, 48 minutes, and 19 seconds. All right? Now, the next thing that we need to do is we have to figure out what the actual azimuth from point 1, from this point here where we're set up, to this point up here at point 2. So we know the azimuth from point 1 to 99 is 309 degrees, 48 minutes, and 19 seconds. Now, to get the azimuth to point 2, all we have to do is add the angle, the horizontal angle we actually turned out in the field, the angle to the right. It is 385 degrees, 33 minutes, and 37 seconds. But we know we can't go more than 360 degrees. So we're going to subtract out 360 degrees. That means the azimuth angle is 25 degrees, 31 minutes, and 37 seconds. Okay? So that is this angle here in red, going from the 0 line out. So this angle here is 25 degrees, 33 minutes, and 37 seconds. So the last part of it is now that I've got my horizontal distance and my azimuth, I can use the equations for departure and latitude. Okay? So departure is the length, which is our horizontal distance, times the sine of azimuth. And the latitude is the horizontal length times the cosine of the azimuth. So departure is equal to 66.75. And notice, just based on the picture, I am sitting here with my instrument and I am looking to the northeast. That means I'm going east and then north. Okay? And the latitude is 154.71 times cosine of the azimuth of 25 degrees, 33 minutes, and 37 seconds. So its latitude, the change in y, or the northing, is 139.58 feet. Now, the last part of this is I have to figure out the actual coordinate x y, or northing and easting, for point 2. Starting with point 1, I know the northing and the easting is 800 and 1500. Okay? And the departure is 66.75 and the latitude is 139.58. So I'm going to get to the easting. I'm going to take the easting from point 1 and add the departure. And to get the northing of point 2, I'm going to take the northing of point 1 and add the latitude. Therefore, the easting is to point 2 is the 1500. This is my easting, northing and easting. So I'm going to take 1500 and I'm going to add the 66.75. And that's going to give me an easting of 1566.75. Now I'm going to take the northing of 800 from point 1 and I'm going to add the latitude, which is 139.58, and I'm going to get a northing for point 2 of 939.58. So the point 2 is going to have a northing of 939.58, an easting of 1,566.75, and a z elevation previously calculated of 53.93. Okay, that's it for trigonometric leveling. If you have questions, send me an email.